This presentation will go over the experiments that we'll cover in October, the guidelines for our modelers who wish to participate, and just a quick agenda of what we're covering. We'll give some background on the main targets and objectives of MaCFP. We'll introduce the timeline of events that we need to work through to make sure we're successful in October. And a bulk of this talk will be introducing the 5 target cases of interest. We have 2 in the gas phase, an extension of the solid phase modeling from MaCFP2, and our first ever coupled gas phase, solid phase fire growth simulations that look at fire growth over the MaCFP solid phase material. We have organized a lot of time for open discussion, as we always do in our workshops. We want to make sure the community can share their questions and provide us with the feedback that we'd like to keep this moving. And broadly, this presentation will be us going over the guidelines for participation document that we shared about a week or 2 ago. This lists all of the target cases of interest. It provides some details on their setup, the experiments that we took, what we want modelers to actually submit. And now is our chance to go through these, make sure it's clear what we're presenting and what we're asking for our modelers to do. As Randy added in the chat, thank you, Randy. This meeting is being recorded. There are specific NIST guidelines. I'm just making sure that you all know that. So just please be mindful in what you present and what you share. Make sure we're not saying anything confidential. And then importantly, this allows us to have a record of this meeting that we can share with participants who can't be here right now because of time zones or need to step out for various reasons. So we will cover the main objectives of MaCFP first, just as a broad background of what we're here for. MaCFP is the Measurement and Computation of Fire Phenomena Working Group, and our core objectives are to develop a digital archive of well-documented and well-prepared fire experiments that we can use for CFD fire model validation, and a corresponding archive of simulation results predicting these behaviors. We would like to develop the protocols that we need to compare these results in an objective way, identify what knowledge gaps we have, what we can simulate well, what we need more work on, and work on best practices for both the experimentalists and the modelers for how we set up our tests, present our uncertainties, document how we run our simulations, and present our results. And I'll say this time again through the meeting, we really do want to establish a network between researchers in this field, both experimentalists, both modelers, to have a collegial atmosphere where we can present these things and do it together versus working in our own silos. And so on the left, as we look at these core objectives, I have a list of the primary phenomena that we are interested in right now. So when we look at the target cases that we're presenting today, or others that we might look at in the future, we are looking to create systematic progress in fire modeling. We want to do that through a building block approach. And some of the phenomena of interest that we have in the condensed phase or the gas phase might be, can we do thermal decomposition well, or charring, or heat transfer? When we look at turbulent flow, or soot production, or scaling, these are the core phenomena that we believe we should be able to do well if we're doing good fire modeling. And each of the experiments that we have in our repository, or that we'll discuss today, each of those should connect to several of these key phenomena and make sure we're addressing them. As we look to expand what tests we're doing in the future, or we look for any new data that's coming in, we should make sure that all of this work aligns with these core goals. Can we predict these things well? As we start doing specific phenomena really well, maybe we can move on to others. And I want to highlight that this is not an absolute and final list, but we can continue to add to it and evolve as needed. This is available at the link on the left on the GitHub repository, and so it's a good time to identify that repository, which is here. This is the core central meeting group where we have
Isaac,
all of our experiments. Yeah.
Can I slow you down just a tick and go back to your previous slide, because this is something new and I'm not sure everyone in the community has seen it or is aware of it yet. I want everybody to kind of take 2 seconds to let it sort of sink in a little bit. So if you go back to almost all of the documentation that we've put forward on MaCFP, there really hasn't been a document like this, what we're trying to achieve here, that actually lists what our phenomena are and how we prioritize these phenomena in terms of what we think as the priorities for us to do research in this community. So the only way to really get at this information would be to go to the GitHub website and then just infer it from what we've listed as the folders at the top level of the repository. So our goal here, this got brought up at some point, and our goal was to take a stab at being a little more formal about this so that we could all try to agree on where the priorities are, what we think of as primary priorities, secondary priorities, rank them, make sure that as new experiments are proposed and so on, that they align with the the priorities and goals that we have here. So this is open for discussion and contribution and so on. So I don't want everybody to think that, okay, this is just something that's been laid out, you know, and set in stone since the first day of MaCFP. So I just thought that was important to bring up at this point.
Right on. Thank you, Randy, for clearing that up. To the repo, though, as we move on, all of the information that we're presenting, our experimental measurements, our modeling targets, the results that we predicted, that's available on a well-maintained and archived and version-controlled repository on GitHub that you can find here. There are two main repositories on the MaCFP repo, the solid phase material database and the gas phase MaCFP database. In the solid phase one, you'll find all of our experimental measurements for material property calibration. So when you develop your pyrolysis models, what tests did you run to calibrate them, as well as the material property sets themselves and results of simulation data showing how well they predict behavior of interest. On the gas phase, we also have all of the core cases that we're looking at. So fire growth, extinction, pool fires, all of that measurement data, descriptions of that data and how those tests were run, our simulation results through previous workshops and the upcoming one, that all lives on this repository right here. So we encourage all of our participants to become familiar with this repo, understand how it works. Always look here if you're looking for the most current data sets that are out there, the most current reports that are available. Many of these things are living documents. So as we update, you know, our set of priorities that we're going for, or we add more information to our README for this or that experiment, you'll find that there with all the information of the tests, the results that are there, the measurements, what we want you to model. And specifically, as we move forward to October, if you are submitting modeling results and you're a participant in that way, we really hope that you'll submit that by a pull request through GitHub. You'll prepare everything in standard formatting. You'll submit that. We can review your pull request. And rather than having a bunch of different Excel files that are shared by email with this or that committee member, hopefully we can do it in a more formalized way, and that will be through the GitHub repository. And just going back to some previous lessons that we've learned over the last few years of organizing this and other databases that exist out there, the metadata that we keep here is critical. So we can't just have a Dropbox full of files. We need to identify what they actually are, how they're formatted, what data is in there, and how these tests were run. Maintaining this database takes considerable effort. So some of the timelines might seem like, oh, we could do it a bit quicker, but there is time and effort into making sure everything works together, our scripts are running, data is properly formatted. And I want to thank Randy, who just hopped on for being a lead and maintaining that. And you know, as we identify all the cases we're looking at, we need to make sure that all of this connects to some application of interest to the fire modeling field. So there's our repo. We identified something about the cases we're looking at. And I want to add a note to our discussion forum. So after this meeting, throughout the coming months leading up to the October workshop, we would like to encourage our participants to go to this page. You can sign up to have updates on what MaCFP is up to, and hopefully you can continue all the discussions that we've started in this event or similar ones. You can ask questions about the GitHub repo itself, the data that's there, the metadata, how we ran this or that test. If you're interested in contributing or participating in future workshops, you can share, hey, we're interested in this data set, or providing some help with modeling or maintenance of the repo. All of these kind of questions we hopefully there to have there to have a vibrant community that brings together our experimentalists and modelers in a nice unified way. And if you're already part of this working group and this discussion forum, you'll have seen 4 or 5 different posts that I just added this morning. All of the case studies that we're looking at that we're going to present in MaCFP 3, there's now a thread for each of them. So if you have questions about the pool fire case, please add it up there. We'll respond to you as quickly as we can, and other members of the community can, you know, see your questions and our responses, and hopefully we can learn from that together. So moving forward, we can share the actual meeting agenda. On October 22nd, we'll hopefully all be together in Japan. We'll have a morning and afternoon session to present our experiments and our modeling results. We've got a lot of time organized for discussion, and we are hoping to also organize a poster session that allows us to further go into some details that we may not be able to get through in the first 2 sessions. So to start the day, we'll have just the gas phase and condensed phase simulations that we're looking at. So our pool fires and our FM burner. or just the model validation exercise for material property sets. We'll present those, the experiments themselves, our best modeling results from there. And then we will also introduce a new radiation heat transfer subgroup that is just getting online and will become part of the MaCFP community. In the afternoon, this is the first time we come together to do a coupled problem. So this is both gas phase and solid phase phenomena of interest to fire modeling. We have two different case studies that we're looking at there. We'll present each of them, we'll present our modeling results, and have a lot of time for discussion on how is this set up, where do we need to go from here. And part of that, what's coming next, will be in the poster session, which allows us to have further time. Instead of just pre-recording a session, you'll be able to talk to other participants, see how they set up this or that model, how they came to their decisions, what assumptions they made. Maybe there's future experiments that they believe can address some cases of interest, and we'll have a lot more detail that we can discuss there together. So open questions. We're just seeding the ideas of things we might want to go into. Maybe there's a pyrolysis modeling exercise. Are we interested in new materials of interest? Are there additional experiments that we need to run? How often should we have these virtual meetings? What can we commit to and what we would like to see? All of these things are things we can hopefully talk together as a community, both today and in future meetings together. So I'll jump to the timeline and then we'll introduce each of our 5 cases. Right now we are here in March. And so we've shared our call for participation. All of the measurement data that we're going to discuss today is now available on the GitHub repo. And we have guidelines for participation that are available as a PDF document that we shared and as a wiki on the GitHub page. So today we're going to introduce each of the cases of interest that we want to study or produce models for in October, and spend a little bit of extra time on this pyrolysis model validation exercise where all the effort from MaCFP2, we have a new data set to hopefully validate the material properties that were presented, and then provide those to our gas phase modelers who are doing these coupled gas phase, solid phase simulations. Hopefully that can all come together by June, the new material property data sets. The committee will organize everything together and present that sometime mid-summer. And then our final flame spread and gas phase and just all of our modeling results for October, we hope to submit at the end of summer so that the committee can then put those together, make sure our plots are working right, make sure we fix all the issues that might be there. And finally, we come together in October. So broadly speaking, these are our targets. I'm going to sit back from talking now, and I'll introduce Dr. Anthony Hammonds, who will go over our first case of interest, which is the NIST Waterloo pool fires. And I'll mute myself. Anthony, if you can come back online, just give me a heads up when you want to jump to the next slide, and I'll progress from there.
Okay, thank you, Isaac. So the MaCFP GitHub website contains data sets representing complementary pool fire measurements conducted at the University of Waterloo and at NIST. And a schematic of the NIST burner system and gas sampling apparatus is shown on the top left of this slide. Fires are established on water-cooled liquid or gas burners, and a gas sample is extracted from various locations in the fire via a pump and mass flow controller. The sample flows through heated lines and a particle filter and is injected into a gas chromatograph mass spec for identification and quantification of gas species. The photo on the right shows the Waterloo 0.3 meter diameter constant feed acetone pool fire mounted on a two-way traverse. The fire is moved under a thermocouple and a 2D laser Doppler anemometer system, and it allows simultaneous mapping of the temperature and velocity over the entire flow field. Fires in both facilities were established beneath canopy exhaust hoods using mesh screens to shield the fires from cross flows, facilitating quiescent conditions. The table on the bottom left lists the liquid and gaseous pool fires in the GitHub database, including 0.3 and 1 meter diameter methanol fires, the 0.3 meter acetone fire, and 0.37 meter gaseous methane and propane fires. These benchmark cases correspond to pool fires that feature moderately turbulent flows characterized by buoyancy-driven puffing instability, which leads to cyclic formation of axisymmetric vortex rings, as seen in the video on the right. I'm not sure why the video is not playing. Could you hit that? Yeah, okay, there it goes. That's a 1 meter methanol pool fire. The table on the left shows that the fires spanned a range of heat release rates from 20 to 250 kilowatts and Q star values from 0.2 to 0.6. The table also shows the dominant puffing frequencies, normalized flame heights, radiator fraction, and peak soot mass fraction measured along the fire center line. The table in the middle of the slide highlights the global and local measurements posted on the GitHub website. The global measurements include mean flame height, dominant pulsation frequencies, mass burning rate using a load cell, heat release rate from oxygen consumption calorimetry, radiative fraction from heat flux gauges, and the yields of soot and CO in the plume using non-dispersive infrared and in situ laser transmission measurements. The local measurements include gas phase temperatures using fine wire bare bead thermocouples, gas velocity using laser Doppler or bidirectional probes, radiative heat flux distribution to the surroundings using radial and vertical arrays of heat flux gauges, gas species volume fractions using extractive sampling and GCMS analysis, vertical temperature profiles in the liquid pools using thermocouples, and the mean heat flux onto the fuel surface using the water-cooled burner as a calorimeter for the gaseous fuels, and a small translatable total heat flux gauge for the liquid fires. The next slide shows representative measurements from left to right. The plot shows profiles of the axial velocity and temperature along the center line above the 37 centimeter diameter gaseous and 30 centimeter liquid pool fires as a function of Z star, the physical position normalized by the pool diameter. The flow field velocity vectors are next to the right of those plots in the 30 centimeter methanol fire and directly below the joint probability density function of the axial velocity and temperature in the 30 centimeter acetone fire. Next, the centerline profiles of CO and soot are shown as a function of Z star in the 37 centimeter diameter methane fire. And then the plot on the right shows the total heat flux profile just above the fuel surface in the 30 centimeter methanol fire. The bottom right plot shows the power spectral density determined from a temperature measurement in the 30 centimeter acetone fire, indicating the dominant puffing frequency in the fire. In aggregate, these measurements begin to build a picture of the structure and dynamics of medium-scale pool fires. Detailed information on the Waterloo and NIST measurement methods, uncertainty analysis, and results are documented in the references listed in the README file on the MaCFP GitHub website. And thanks for your attention. I look forward to any questions.
Thank you, Anthony. So we'll jump through all 5 of our cases. I'd like to move on to Yi Wang for the FM burner that's coming up next. I'll mute myself again so you can step on in.
Can you hear me? Okay.
All good.
So, okay, good. Yeah, thanks for the opportunity to introduce this experimental setup. The work has really been done by my colleague Dong Zheng and Gang Xiong throughout the last maybe 4 or 5 years. It's actually a round burner with the inner diameter 13.7 centimeter and outer diameter 15.2. So I want to emphasize, these 2 diameter because later on when we have a measurement location, we're actually using the outer diameter as a normalized height. But for modular, maybe we should know the inner diameter, so making sure the fire base is correct. The burner is putting in the enclosure of about 1.2 meter by 1.2 meter dimension and 1.8 meter high. We're using that enclosure because we can control the cold flow and the inside oxygen concentration. So basically, we varied oxygen concentration from a normal air condition, actually all the way to about 11 or 10% by volume to induce extinction for different fuels. But here we only specify up to 15.2, where we actually measure the detailed flow field. I'm going to state the reason why we're only up to 15.2 a little bit later. The fuel we are using here is ethylene. We also have different other fuels, propane, methane, and I think there's another one, 4 different fuels. We had 2 fire size 10 and 15 kilowatt flame, and the one with a lot of more diagnostics is a 15 kilowatt flame. So if you click the video on the right-hand side, yeah, you actually can see a little bit visual of this flame. Just a little bit background, maybe can we advance to next slide? Yeah. A little bit background of why we do this. At the beginning, we really want to study extinction and reignition phenomena in bond turbulent flame. So that's why we designed this enclosure. We control cold flow very well, and it's big enough so that we make sure all the ambient have the right oxygen concentration. We really want to study extinction. However, when we starting to do that, for the extinction data, we're only getting the combustion efficiency, global combustion efficiency. And those reduction of combustion efficiency really only being achieved when oxygen concentration is very, very small, about 12% roughly in that range. And there's a very sharp line. So, about that location, the oxygen, the combustion efficiency is close to 1. So, however, we see significant change of luminosity, basically the radiation change, the soot generation change. We thought, before we really getting a lot of quantitative data for extinction, let's look at the radiation and flame soot generation for different oxygen concentration. That's actually one of the major information in this database at this point. I just want to emphasize we are still working on extinction now, and recently some work being discussed in the National Combustion Meeting, and we want to getting more quantitative data for extinction and reignition, really at a lower oxygen concentration, but some of the data are not available yet. We only have a combustion efficiency at a global measurement. Again, other than combustion efficiency, we have radiant fraction, which also change with oxygen concentration, and radiant power distribution, which is actually the curve you can see in the right upper corner, where x-axis is the height and y-axis is the power, radiant power per unit of height. You can see the distribution, along the height, and also you can see the variation with different oxygen concentration. Is certainly reducing. When we're reducing oxygen concentration, especially when you're going to 17, 15, reduction is very clear. Okay, some local measurement. The first set of experiment data in local is actually radiation intensity measured by a two-color emission probe at a different location in height and profile radio location. Basically, you would have the whole turbulence time series of turbulent radiation intensity, and then we backfigure what would be the corresponding soot temperature and volume fraction using this two-color radiation methodology. And also we conduct LILI measurement of soot volume fraction, and also compare, that's also 2D soot volume fraction data. We compare this data set with our probe and also with extinction, finding some mostly consistent data other than small area near the burner. And we also measure the temperature and velocity. The temperature data have been published in a separate paper in the last symposium, but we only have air case been published. And we actually are working on addressing some issue about thermocouple measurement, which I think we fix the problem. Then we should have a very high fidelity data for reduced oxygen, should be available very soon. For velocity, this we using PIV. This data is should be available very soon. We just mapped all the flame for the different oxygen concentration. We actually submitted a paper into this symposium. Hopefully, it should be available very soon. We should be able to make the data available in our database. That's basically the data set. As you can see, you have a lot of flow field data, temperature, velocity. Hopefully, we're getting fluid mechanics correct. And we're getting some soot and radiation temperature data by different measurement. And we have some global measurement for radiation fraction, radiation power distribution, and also have combustion efficiency toward extinction modeling in the future. Okay, that's all I want to say. Be happy to answer any questions.
Great, thank you. Just for completion, we also have, we'll share this PDF later, but these are the specific modeling targets that go with each case. We'll highlight those. But I think we had a great walkthrough of the experiments themselves. And if I can pass this over to Morgan Bruns as we go from gas phase to solid phase, we will return back to the MaCFP PMMA that we first looked at MaCFP2. It was a nice, suitable first reference material. It didn't melt, it didn't drip, it had simple decomposition kinetics. And Morgan, I'll lead you this slide. I don't know if you want to hop onto the next one right away or say something else here.
No, I think that I'm ready to move on. Hello?
I think you have power for this one now because you have annotation ability.
Okay, got it. All right. I can't forward. Okay, there we go. Thank you. All right, so yeah, the next cases that we're going to talk about today are coupled gas phase and condensed phase cases. Historically, for those who don't know, MaCFP started out primarily looking at gas phase modeling, and then at the first MaCFP in Lund, we started discussions of how we can incorporate condensed phase experiments and modeling to help support development of combined gas and condensed phase fire modeling. The first real results of the condensed phase represented at the last MaCFP2 with the MaCFP PMMA, and the objectives there were really twofold. One was to give this material. Isaac did a lot of work to distribute this material to people around the world, and they did various experiments on it, primarily the milligram scale standard tests, TGA, DSC, MCC, along with some a larger gram scale cone calorimetry and gasification. So the output of all of that was sets of material properties describing this nice black MaCFP PMMA. The second side of it was we didn't want to just let people get the properties. We asked them to say, well, what did these properties tell you about how you would predict TGA kind of beyond the regime at which you obtained the parameters, but then also in gasification tests. We'll talk more about this in a second, but I want to emphasize that these results that were presented were strictly predictions. There was no data to validate them against, and so that's something that we're going to be remedying in the next case that Isaac will talk about. So we had really good participation. We had property sets delivered from 9 different institutions from various places around the world. We received 12 complete property sets. And by complete, I mean that they would have everything that you would need to incorporate into a fire model to predict the pyrolysis and heat transfer in this material. And then we had 7 pure kinetic property sets. So we had some labs that contributed just analyzing TGA data and figuring out how we could describe the pyrolysis kinetics. All of this data is now available on the MaCFP GitHub repository. There's a link there at the bottom of the slide, so please check that out. I should mention my visuals, I guess here. These slides. I'm just now playing around with my little drawing tools, so I'm not sure exactly what does what, but I'll try this. So the first plot up here is the results from all of these labs of their kinetic analysis. So this is the pre-exponential versus activation energy from these, I guess, 19 total property sets describing pyrolysis kinetics. One nice thing I want to mention is that we already know that this data has been used. Rich Lyon just sent a paper out that he analyzed the MaCFP PMMA data in a paper where he was talking about this nice kinetic compensation effect. So it's good to see that this data is getting used. We also had things like this thermal conductivity as a function of temperature, just to show you kind of an idea of what people produced. A lot of it is assuming constant thermal conductivity with temperature, and then a few labs did temperature dependence. So all that information is available, like I was saying, on the repo, which when you get these slides, you can click directly to the link, or you should be able to find it now. One thing about the way the data is stored, which is a little non-standard, it's stored in text files, in particular JSON text files. So JSON stands for JavaScript Object Notation, which is a widely used way to just represent data objects now. It has the advantage of being easily parsable by most programming languages, but also human readable. So if you're looking, and this is just a snippet from the property set provided by Alto, they have material name specified, the lab who created this property set, and then the first main block of this data object is metadata about how they obtained the properties, and this is listed under calibration. So what model did they assume, what method was used, what was the scope of their calibration, so what did they fit over, it was defined kinetics against TGA at different heating rates from Lille. So this information is in there, plus the actual properties themselves. I didn't list them there because they're, that's more straightforward to a large extent. So all this is available. You can go to MaCFP, you can get these files, you can get properties for this MaCFP PMMA. That's interesting in its own right, just because it's a large data set. That's, I gave the mention of the paper by Rich Lyon, so there's a lot of use in that. But in particular, it's going to be hopefully useful for the next cases that Isaac, that other committee members are going to talk about. I'm still not sure how to proceed in my slides here, Isaac. Are these all marked up still?
Let me see if I can clear all of that, but for now, yes.
Okay, well, I think I have an eraser here, so thanks. All right, so the second thing that I mentioned about what was done at MaCFP2 is that we made these predictions. And as I said previously, these were predictions of TGA and slab gasification. They're predictions, not validation. We don't have anything we're comparing them against. This plot on the top left is the summary of kind of the TGA predictions. We asked people to predict TGA at 100K per minute. This scatter plot on the right shows information about the peak in one of the gasification predictions at external heat flux of 25 kilowatts per meter squared for a 12 millimeter thick sample. All of these data sets are also available, and if you click the links on these slides, you can find all of these CSV files describing mass and temperature for the TGA and gasification tests. Now, the last thing I want to say is that it's come up that we've done all this and we produced all these material property data sets, but as I've mentioned several times now, there's no validation, so we can't really say, we recommend this data set. And I don't even know if that's the point of this collaborative effort to begin with. but modelers would like to know. They want to model coupled gas and condensed phase scenarios. So they want to know, well, what properties do I use to describe this PMMA? So kind of the stopgap measure that we have in place for that is we determine a most average property set. So I don't know if that's a previously used technical term or not. It's probably not ideal, but what we mean by this most average is that it's the property set that fits closely to the mean of all the predictions that we've obtained. And so the gasification data sets were averaged over time, both in terms of their mass loss rate and their back surface temperature. And you can see in these slides when you have them, I don't know how well you can see it now, but there's a mean curve in the middle where these are just average of these time series representing, I suppose, the mean predicted by the different labs. And then using a fit measure proportional to the sum of square errors, we found which data set predicted data closest to this mean. And we found out that it was the University of Maryland data set. So if you go into the data sets mentioned in the previous slide, and you want to kind of have some idea of what you would use as just something that's representative of all the data, this is what we're going with now. So if you want to get started on modeling these coupled cases that will be talked about in the next slides, this is the most average property sets that can get started. Now, as Isaac will mention, there's going to be an intermediate step where we are going to have validation of these different data sets in terms of their predictions of gasification data. Then you'll have more flexibility in choosing ones that are validated against the data. So I want to emphasize, we're not implying that this Maryland property set is the best. We don't know it's the best. We just know it's most representative of what everyone's predicted. So sorry for scribbling all over these slides in a way that can't be erased, but thank you for your patience. And that's all I have.
Good. Thank you, Morgan. So I will jump from here, going from what we did in MaCFP2 on the solid phase to the validation exercise we had moving forward. A big goal of this, as Morgan pointed out, was if you're doing these couple of simulations of fire growth and flame spread, a modeler is probably going to want to have a property set that they can just plug into their model. So as we get to October, right now, if you're just setting up your initial models, start with this most average data set, and the exercise that we're going to present is going to allow you to say, all right, well, here's a validation set of data. Let's use these same properties to predict, let's say burning behavior or thermal decomposition in known heating conditions. And then we can better identify which one's best at getting onset of decomposition or average burning rate or temperature and heat transfer through the material. That's what this nest case is looking at. So we can identify there's a good bit of scatter here. We're not going to say that one data set is necessarily better or worse, but they probably aren't all right. And so we spent the last year or two trying to identify, well, what's a good instrument that we could run validation experiments in that we could then use those properties to predict this measured behavior in and hopefully validate those results. And we settled on the old NIST gasification apparatus that was first brought to life probably 2-3 decades ago by Takashi Kashiwagi. This instrument is powerful because it provides very well-controlled boundary conditions, so we know exactly the amount of energy coming into our sample. This is all done in an anaerobic environment with pure nitrogen down to 0.00% oxygen. The walls are perfectly water-cooled. It's really nice and stable. We characterize this well. And importantly, no data set submitted in MaCFP2 use this apparatus or something exactly the same for model calibration. So hopefully it offers an independent data set for validation of the results that have already been submitted. So we took a year or two and we replaced a whole bunch of key components. We upgraded our measurement system, our ability to record data and video. We replaced some physical components just to keep it working well. And then we carefully characterized the boundary conditions in this apparatus. As you'll see, there's roughly a 30 centimeter diameter cone heater that will heat up your test sample. And once you load your sample and you purge the system of nitrogen, there's a water-cooled shutter that sits in place there, but once everything's ready to go for the test, we remove that shutter and expose our sample. What the sample will then see is a heater time response as we have here on the left. So on the x-axis, we've got our time after shutter removal. On the y, we have the normalized heat response, in this case at 25 kilowatts a meter squared. And we see all across the different surfaces of the sample pretty much the same time response to that heater. And once we get to steady state heating, about 300 seconds after shield removal, we see a heat flux profile across the surface of the sample as we have measured here. So this comes from measuring heat flux here and here and here and here at 20, 30, let's say 21 to 28 different points across the surface of the sample. We measure our time response, we get to steady state, we can get this nice heat flux map, and we do that both at 25 and 50 kilowatts a meter squared. So we have our incident heat flux that we want to apply across the surface of the sample. Roughly 97% of that sample is within 97% of the target heat flux that you would want. So we've defined that well. We've carefully characterized chamber wall and gas temperatures near the sample, and those are very stable as we're running our tests. And we will take a 7-centimeter disc of the exact same MaCFP PMMA that we used back in 2021. We will mount that to a sheet of rigid insulation, put that on top of several more sheets of insulation, and put that on top of a mass balance that sits right here. I want to note that the nominal thickness of these PMMA slabs is about 5.8 millimeters, but it does vary from test to test, anywhere between 5.3 and 6.2, 6.3 millimeters thick. And that has a noticeable impact on our measured, total burning time or gasification time, and on the measured back surface temperatures. So it's not just random scatter. We carefully characterize this in the metadata that's available on the repo so we can interpret our measurements better. And so we'll prep these samples, they're cut to size, we store them in a desiccator after mounting them to their insulation. In between our sample and that insulation layer is a thin, maybe 1.5 gram layer of epoxy that holds it flat during our tests. Once that's been set and pressed and stored for a day or two overnight, we can load that into our chamber, purge the system of nitrogen, get nice steady heating conditions from our heater, and finally expose the sample to the heat flux of interest, either 50 or 25 kilowatts a meter squared. And then the measurement data that we're collecting will either record sample mass, the whole thing is sitting on a load cell, or in separate experiments, we'll record temperature at the back surface of the sample with these two thermocouples that are roughly 0.5 centimeter away from the center of the material at its back surface. We have photographs and video from a top view on this camera and a side view here. And additional validation, we also put samples of copper and cable insulation and exposed it to the exact same heating so that we can provide measurement data of temperature of materials that have known thermophysical properties to help you calibrate and validate that your model predicted boundary conditions would provide the conditions that you've measured for a known material. So this is our whole setup. It's a very nice, well-controlled, well-characterized apparatus. We provide the following information for you. I'm just going to focus on 50 kilowatt data for now, but we can look at measured sample mass in triplicate tests. You'll see the initial sample mass is here. We heat it after about 60 seconds, it begins to start gasifying, and we go down to negative masses because this is equal to the mass of the epoxy holding our sample to that back insulation. We can look at sample mass loss rate. We have back surface temperatures that arise here, again, 4 or 5 different tests that we have. And we'll note just a minor thing, but it's something to be careful with. Depending on the thickness of our sample, we'll have slightly different mass loss profiles or temperature profiles, with thinner samples heating up a little bit quicker, thicker samples taking a little bit longer to heat up. And those thicker samples also, excuse me, I'm in a meeting. Can you come back later, please? Right. And so those thicker, longer samples will also burn for a little bit longer, as we see here. So when you look at these tests, please don't just think of it as random scatter. We provide the metadata for exactly the initial mass, how much epoxy was there, how much sample was there, how thick it was. That's available on the repo. And then for our pyrolysis modelers, the exercise that we'd like you to do is take this data that we have here and start with the original property sets that you produced from MaCFP2 and just validate those results. It doesn't matter if it's perfect or not. We just want to take that property set that you have and reproduce these measurements that we have here in a unique apparatus and see how well we're able to predict that. Maybe you get onset of decomposition time really well. Maybe you have steady burning well or the burn time well. Let's see what these models are doing well and what we can use them for. And as we noted, or as Morgan noted, there's variation in the predictions of these material property sets. And while we can't say any one of them is right or wrong, it's unlikely that they're all perfectly right. So let's use this new validation data to see what's working well or not. And then Based on your results, if you've got great agreement, then great, go ahead and use those models. If you see, oh, well, my model might predict this burning rate, or I'm way up here and then it dies down, that might be a clue that you want to revisit the assumptions that you made when you calibrated your model. Maybe you fit it to a data set and you assumed this boundary condition instead of that one. And we would like our modelers to first blindly predict these validation data sets with your existing models. If you don't think they're perfect, please go ahead and recalibrate them, but make sure you're being really careful about your calibration data and your validation data. Please revisit your TGA data sets or DSC or Cone or FPA or whatever you used before and say, oh, we made this assumption and we think it's better to do this now. And that's why we're changing our results. And then separately use your new data set to blindly predict this validation data. So hopefully it's clear on the calibration versus validation part of this. I want to highlight that if you were not able to participate in MaCFP2, we're still more than happy to have new models submitted for this exercise. Just please be careful, don't fit perfectly to this data set and say, hey, I match it, it's great. Please use the calibration data that's already available and develop your models from there. All of this we hope to get from you in 10 weeks on June 1st. The simulations of this data with the original MaCFP property sets, new material property data sets that you believe fit things better, as well as simulations of these gasification tests and an explanation in your README of how and why you tweaked your model. And then in midsummer, we will share all of these results after analyzing them for a couple weeks. We'll have one more virtual meeting where we share this with the community and say, here are our new property sets. These predict decomposition well, maybe onset of decomposition or burning rate or heat transfer. Here's what they predict well. We won't specifically say this one is best, but we will give you objective tools to say what they do well and what other models might do better. And then you can use those for your couple of flame spread simulations. Hopefully this is all clear. I can now jump over to Stosilov at the University of Maryland, who will introduce our first coupled flame growth, fire growth flame spread case, and I will mute myself as we get there.
Can you hear me, guys?
All good.
Okay, thank you. So this is a test where we looked at the flame growth on in a corner of PMMA panels. So those two panels have the same average thickness of about 0.6 centimeters. They are about 1.5 meter tall and are mounted in a corner configuration. The panels are ignited by a propane burner that is run at 30 kilowatts of heat release rate. The setup from the point of view of panels and the burner, so the panels are about 50 centimeters wide, and the setup is symmetric with respect to the plane bisecting the corner. So that's the most significant difference between this setup and actual single burning item test, which is not symmetric. The whole setup was placed under a hood, under a curtain, with a small opening at the bottom, which represented a fire mesh to make sure that there is no any errant airflows that affect our results. So the key measurements that were performed include heat release rate measurement, and one thing that we were ensured of is that the response time was sufficiently fast to ensure that all the features of evolving heat release rate are represented. We also measured flame heat flux to the surface of the panel, to be exact, to the cold gauges located flush with the surface of the panel. And we performed that at 28 different locations, pretty much mapping the heat flux imprint of that flame on the surface. So global heat release rate, heat flux to this panel. We did some videography that we collected at a monochromatic single wavelength of 900 nanometers, and the idea was to focus on the emissions from soot, and we provide some quantitative information about that in our data. And finally, we performed measurements of the radiant heat flux away from the corner. The figure on the bottom right shows you where this radiometer was located. It was actually a set of radiometers located across the height. They facing the center of the corner, and what they basically measured the radiations from the flame itself, it's also radiation from the panels. So the heat flux gauges on the panel walls were designed to measure heat feedback from the flame, consisting of convective and radiative components. And the heat flux away from the corner was result to measure only the radiative component. And our hope is that it will help you better resolve convective and radiative components of the heat flux from the flame by doing that. I think that that's the essence of this test. Isaac, can you move to the next slide then? Okay. So there were about 10 tests performed. I think, if I remember correctly, the heat release rate was measured in 7 tests, and then each information on the heat fluxes was measured at least twice, so the repeatability was checked very carefully here. What we would like the modelers to deliver for this particular case are, of course, global heat release rate, instantaneous flame shapes that can be compared with our snapshots from our videos of this growing flame. Just to reiterate here, the flame here grows up and sideways. So we're talking about buoyancy-driven flame spread upward and also creeping flame spread sideways. So there's 2 forms of flame spread that operate here. We also like you to reproduce heat fluxes to the cold heat flux gauges located along the panel. The figure on the bottom left shows you the one, the figure on the bottom left shows you representation of these heat fluxes at 3 different time points. And the figure in the middle shows you the intensity reading from the infrared 900 nanometer camera that we collected as well at the same time. And those both are sort of projections onto the surface of a given panel, because our system is symmetric with respect to the corner. They are identical on each of these sides. So these are the key data that you can compare with experiments. And then in addition to that, we would like to receive a set of data that would help us compare the models between each other. And those include variations in the fuel mass loss rate, surface temperature, convective and radiative components of the heat flux to the surface of the material, variation in the mean and RMS gas temperatures and velocities in a particular specific directions or specific positions that we actually specified in a more detailed document that has been, I think, communicated to the community at this point in time. So that's all I have. I forgot to mention one item. I object to labeling UMD data set as average. I much prefer central.
Got it. Thanks, Sas. Alrighty. Thank you for that overview of our.
I think there was a question from the chat about whether the flux data was instantaneous or time averaged over the 5 seconds that was shown.
Sure, Stas, would you answer that one?
Yeah, so the time was averaged in I think the 2-second intervals, if I remember correctly. I think Dushan here, who is on the call, who actually did all these measurements, may provide more accurate information, but we have much more time resolved data than what's presented here. Here are just snapshots at times where we felt that would best represent the dynamic of changes in these heat fluxes. But originally they were measured, I think, at the frequency of 4 Hertz. And then we beat this data to, I think, 1 or 2 second intervals, I forgot. So that's how the original looked like.
Great. Okay. So I have a warning message saying that everything is frozen, but could you let me know if you're still seeing slides change? Do you hear me saying anything?
Yep, I hear you and see slides changing. So
All right, well, that's a WebEx issue on my end, but as long as you can see, that's great. I'll introduce the second case for fire growth, which has some similarities to the ones that was just described. It is the same MaCFP PMMA that we looked at before. In this case, we're looking at flame spread over parallel panels, so panel 1 and panel 2. And I want to
say
start
that.
back.
Sorry, I will say that there is something frozen at the top of the title.
Yeah, that's all I see. So I'm sorry that this is stuck here. I'm afraid if I click quit, it's going to crash the whole thing. So if we ignore the cover slide, you'll see all the content at least below. So we ran these tests at NIST in the large fire lab, the National Fire Research Lab, which is run by Matt Bundy. We want to thank them and their technicians for making these tests possible. I need to acknowledge the NRC for their support to do these tests. We looked at roughly 20 materials for them, and we'll focus just on the MaCFP PMA here. And of course, this apparatus is originally designed based on the FM 4910 test standard. So we're looking at almost 2.5 meter tall samples. They are 60 centimeters
I lost
wide.
this
Now you have
picture,
lost
Isaac.
video.
Yeah. All right. You are both co-hosts. Morgan, do you mind taking over from here? And I'm just gonna quit and come right back in.
Sure.
All right. I'll be back hopefully in a minute.
While we wait for Isaac, there was a question asking if the PMMA and the SBI corner test from Maryland is the same as the MaCFP PMMA, and wanted to confirm that it is. So for these experiments, we're hoping that people are going to use the properties obtained for the black cast PMMA from MaCFP2.
Yes, it's the same PMMA, and also there is a Marinite. It's a calcium silicate board that this PMMA was mounted to, and the properties of this board are also known. So we have that information on that as well. So not only the material is the same, and the properties are defined. So we studied the same materials, all of us. We also have information on the backing material. And that,
Celestine, do you know if those properties are included in the README on the MaCFP site, or do people need to reach out to you to get those?
I have to check that. I'm certain that the reference to the paper where this material is published does contain these properties, but I don't know with certainty whether we included it in the description. I have to check.
Okay, thank you. And sorry for using most average. It wasn't implied to be a evaluation of the property set.
That's okay. That's that's it. Totally.
Can I ask a question about the UMD SBI, your test?
Of course, I know.
So the experiment is stopped at some point. Can you explain us, why this time for stopping the experiment, and is the PMMA fully consumed anywhere along the plates?
No, PMMA was not fully consumed, and we strategically stopped the experiment at the point where the panels of PMMA start to decouple from the wall.
Okay.
As long as the PMMA stayed flat to the surface and fully mounted, and here we measured this data, but at some point in time, the PMMA sheets start to warp, and at that point, we usually stop the test. So all the data that were collected showing you the portion of test where PMMA was not warped, it was not completely consumed any part of the material.
Thank you.
So I have joined. I am not allowed to share content in my own meeting, which is a new one for me. Any of the community members who has a PDF copy of the slides, do you mind opening that up real quick? I apologize for whatever's happening here with WebEx.
It's not letting me, so someone else needs to.
Oh, this is silly.
I think perhaps you can describe it in words, and then you just send the presentation along to get to people. That's the most.
Yeah, that may be what we need to do, unfortunately. We were getting to our final slides, so I'll march forward that way. And if any committee member, if you're able to share content, throw that on whenever possible. We've got 6 co-hosts. Hopefully one of you can do that. And for now, I'll just walk through the data that we have on the parallel panel setup. And then Morgan, can I ask you to share a link to the GitHub repository for the parallel panels in the chat box, and at least people can load the data and images that are there and they'll scroll through.
I think WebEx will allow me to do that.
Hey, good. Something. All right, so apologies for technical difficulties, something with WebEx on my end. We were describing a new parallel panel test setup, which is another fire growth scenario similar to the SBI test that Stas just described. These panels are slightly larger. So we are looking at 2.5 meter tall panels that face one another, ignited at their base. Hey, perfect. Would you go back one slide, please?
I will try, sorry.
Thank you.
I have no idea what I'm doing.
Perfect. Well, we have something. Thank you, everyone, for the flexibility in making this work. We have a sketch of the apparatus on the right. You won't see my marker, but that's okay. That's where we are today. These panels are ignited at their base by a propane burner that nominally reaches about 60 kilowatts. It takes 30 or 40 seconds to ramp up before it gets to that steady heat release rate, but that's okay. We've characterized the heat release rate of that burner. We've characterized heat feedback from that burner to the panel walls. And so in this setup, we've lined 6 millimeter thick samples of MaCFP2 PMMA on either wall. They're insulated at their back surface. The entire assembly is put underneath a 3 megawatt calorimeter in the NFRL. And this allows us to produce time-resolved measurements of heat release rate, soot generation, and gaseous species seduction, mainly carbon monoxide and carbon dioxide. I would have wanted to sketch out on the panels where we're measuring flame heat flux, but at 9 or 10 different heights across the panel walls, we measured centerline flame heat flux. We measured with resolve measurements as well. And this is total flame to wall surface heat transfer. We also have a heat flux gauge positioned approximately 3 meters away, and that gets radiative emissions from the assembly to an external target. With initial and final sample mass, we can estimate our heat of combustion. And we've got video and photos of this panel as it burns from a number of different locations. I should note, unlike the SBI, we let these samples burn until complete burnout. So we'll see a large increase in heat release rate all the way up to about 3 megawatts. And then as the samples start to thin out and they lose their attachment to the panel walls, they eventually do fall down, and we see the decrease in measured heat release rate then. At the bottom right of this screen, we have 2 plots of burner flame heat flux to the wall. The one on the left looks at height resolve profiles at the center line. So you can see going from pink to green to blue to black. This is just later and later in the test, from ignition to steady state burning behavior, flame heat flux at different heights across the bottom surface of the panel. So that varies as a function of time. And at the bottom right there, you can see spatially resolved profiles once we hit steady state. And Beth, would you jump to the next slide, please? I point out these measurements because they are our first validation target or modeling target that we want our modelers to produce. So in the middle left there, we note these propane burner measurements that we would like you to reproduce. And we have provided the measured heat release rate that's there. And we would like our modelers to share the flame shapes that they predict, compare that to the videos that we have, and also share total flame heat flux along the center line, those time resolved values that we showed in the previous slide, and the steady state flame heat flux across the bottom of that panel that you can kind of see poking out to the bottom right figure here. For the parallel panels themselves, the PMMA when that's burning, we have a series of different measurement targets that we'd like you to reproduce if you're a modeling contributor. Total heat release rate as a function of time, as you see in the figure at the bottom right, that's plotted on the left axis. and flame shape profiles, as you see in the images there, as well as radiation heat transfer at a distance, which on the bottom image you can see mirrors the rise and fall of measured total heat release rate just on the opposite axis. There is a walkthrough that I wanted to have on our flame heat flux measurements at the top left. So the profiles that we see there from left to right are different fire sizes from about 100 kilowatts right after ignition all the way up to 2,800 kilowatts when we hit peak heat release rate. And at the center, there's a corresponding average flame heat flux profile at the center line of our parallel panels that goes with that. So you can see as on the x-axis, let's say, that's plotting flame heat flux. So the farther to the right, the higher your heat flux is. On the y-axis is height above the base of the panels. And you can see starting all the way at the left, when the flame is only covering half the panel, we don't see heating at the higher heights. But as that flame continues to grow, get larger and larger, and then as it thickens and the whole volume is filled with flames, flame heat flux that we've measured on average across there increases as well. We've requested that modelers predict these flame heat flux profiles as a function of fire size or heat release rate rather than as a function of time to decouple the two effects. If you're predicting a 1 megawatt fire, you should hopefully have this flame heat feedback profile. But maybe in your model, things spread a little bit faster or slower. So we're going to compare our flame heat flux measurements as a function of heat release rate and that real fire size rather than just the time at which we're predicting it happens. And at the bottom left, our final modeling targets that we're hoping people can share. We have additional measurements just for model-to-model comparison, and this includes centerline fuel mass loss rate, surface temperature, the convection radiation split, and also mid-panel measurements of mean and root mean squared gas temperature and vertical velocity. We did not have the ability to measure all of those things in our tests. We can definitely compare our models between them when you submit your final results. So there's our parallel panel test. Beth, do you mind jumping to the next slide? And thanks for taking over here. In summary, we have 5 new target cases for MaCFP3, the 2 gas fire cases that Anthony and Yi presented, a model validation exercise with condensed phase material decomposition measurements, and the 2 fire growth cases that we just looked at, UMD SBI and the NIST parallel panel tests. If you could jump forward one more time. These are our targets that we hope everyone can reach. So in the next 10 weeks or so, we would like condensed phase modelers to take the lead. Please use the parameters that you produced in MaCFP2, reproduce the validation data that we have here, and if needed, recalibrate your data with calibration data that exists, and then separately validate that it works to produce the gasification apparatus data shown as our 3rd case study here. We have additional code-to-code comparisons or model-to-model comparisons of how well your model reproduces idealized decomposition. So 3 different heat fluxes, 2 different sample thicknesses. These were the plots that Morgan was showing before. We believe as we have this better validation data and we can identify what's working or not, we should see better agreement now and less scatter in these results. This is requested from our solid phase modelers by June 1st. In the interim, if you are a gas phase modeler or you're looking at the fire growth simulations of SBI or parallel panel, we encourage you to start with the most central data set from Maryland for now. We can set that up as our base case of material properties. And midsummer, after we've completed this pyrolysis model validation exercise, we'll identify the cases that predict ignition best or burning rate or heat transfer well, and we'll come back together and hopefully by October, we'll then have simulations of the most central data set for material properties and the quote unquote most accurate as you've defined material property set. And that'll allow us to understand the sensitivity of these predictions just to the material properties that are going in. All of that will hopefully come from participants by the end of summer. So the gaseous burners, the flame spread results, we hope that you can submit that at the end of summer to allow the committee time to work with that data, analyze it, make changes as needed, or ask for adjustments. And then, Beth, can you go to one more slide forward? We're here for open discussion. In the guidelines that were shared and also what's going to be available on the GitHub repository, we noted specific points of contact for each of these cases, whether it's general MaCFP questions, questions about a specific case of interest, or questions about how to work with the repository. That information is available. If you go to the little link at the bottom of this screen, the discussion forum, you'll be able to log in there and ask questions broadly to the community. But for now, we're still just holding on with some amount of video presentation. If we can open the floor to questions from whoever's here, and hopefully we can work through experimental questions, model setup, timeline, anything that you have for us while we're here together.
Isaac, Tristan has a question on the chat about whether or not the videos are available for the parallel panel tests.
We can work on finding a way to get those up there. They're available on an internal database right now, and I'll work on making them available for the broader community as soon as we can. I can't promise it this week or next, but I will keep you posted on that one, and we'll get them there by midsummer.
Yeah, the photos are on the GitHub site, but I don't think the video is, so.
This is about hoping you hear me. Comment on the GitHub site. It'd be nice if for all the experimental data, if there was a README or something that made it clear what the data is, you know, the time average, instantaneous, just so that no one misses the data represented.
Jason, I think I heard your question. Was very quiet on my end, but I think it was related to clarity on the data, whether it was time averaged, how it was processed, and some more information on what our experimental data sets look like.
Yeah, I mean, right now, I mean, you've got a bunch of CSV files. There's nothing that mentions, you know, instantaneous data or average data over the interval, just so that we go at modeling and, you know, comparing, you know, making an assumption about what's not there.
So that's a great question. If in the data itself, just the CSV files, the information isn't there. But if you go to the documentation section for any of the experiments of interest, and let's take the panel walls or SVI, there is a detailed description of how the measurements were obtained and averaged and processed before they went into the CSV files. And some of the cases include additional references to tech notes or published journal papers that can detail that in several pages. So for each of these cases, if you go to the repository and click fire growth and click the UMD SVI tests, you'll find several folders, one that includes data, one that includes modeling results, and then one that includes the documentation. And that should have your README of how exactly these tests are run and what those measurements represent.
Yes, and that's for clarity, since this relevant question was asked earlier.
For example, the SPI file in their heat flux doesn't state that it's the time average over the interval.
It does. If you go to the document that is accompanying this file, it tells you that the data were collected at 10 hertz and then being in 2 seconds.
Okay, I'm missing just multiple sections that discuss heat flux. I was looking at.
I'm sorry, Jason, I cannot really hear you.
Oh, then there's 2 sections in the document, one that talks about measurements and one that talks about data file. The data file section doesn't mention averaging, but the measurement does. So that was my confusion, not looking at the right document section.
Right, but the information is there and it should have any details about processing. But if there is something that we're missing there, we should be able to add it as needed.
Do we have any further questions, whether it's the measurements, the modeling targets, just the timeline, how we're setting this up, any further suggestions on any of this process that we've been through here while we're still together?
Isaac, there is one point that I'd like to clarify, and I'm sure you said it, but I want to just draw a difference between our 2 cases a little bit more clearly. I think the main, so aside from obvious difference of geometry, right? The NIST experiment is larger, It's 2.4 panels, and those are parallel panels, whereas UMD experiments is an upright corner. The other difference, I think, and you correct me if I'm wrong, is that at UMD experiment, the propane burner is on throughout the duration of the test, whereas at NIST, the burner is turned off. Is that correct?
Yes, that's correct. There was a video I hope to show of that. I unfortunately did not have that chance, but at 2 minutes in our experiments in the parallel panel, that burner was turned off. And so when you look at the heat release rate plot there, you'll see a brief decrease in fire size before it ramps up again as the flames spread across those panel walls.
So it's a significant difference in dynamics. So I want to point out to everybody else that the difference exists.
Thank you.
So Isaac, I mean, I'm looking at that test documentation. So it says, I see where it says you turned off the burner, but it doesn't say 2 minutes, at 2 minutes, at least where I'm looking. As modelers, what should we use as the point at which we turn off? I mean, are we just going to use 2 minutes, or is there, a specific heat flux or heat release rate?
I think the appropriate way to best match the setup would be to shut it off at that same time. If you can, I can add that to the README. Part of that timing goes to discussions that we had a couple months ago on burner configuration. So I don't want to get into that and add more detail that might be confusing now. But in short, I will add to the documentation a specific timer or event marker showing this is when the burner was turned off to help with modeling.
Okay, thanks.
So is there a way, because now we have quite a number of cases and the documentation is also quite extensive. So is there a way really to just identify updates as opposed to have to reread everything every time?
So all edits are version controlled on the repo. So
Yeah.
you should see that as long as if you're looking at measurement data and you look to that current day, that will tell you if anything has changed, and will tell you by folder and by case if anything has been updated.
Yeah, so I wanted just to follow up on that. I think anyone who's interested, I highly encourage you to star or watch the repository. So in GitHub, there's a way up in the upper right to watch or star a repository such that you can get email notifications when anything changes. I would say that if anything of like major significance changes, that it's on us as a committee to broadcast that information. But there may be little details that we don't want to spam everybody every single day with a major email. So while I'm talking, I guess the one thing that I wanted to bring up before the end of this meeting is just, I'm not sure on the timeline we quite say yet when we need to make sure that modeling results are submitted, because ultimately we need some time to be able to process them and get them ready for presentation at the meeting. So I think same as last time, please plan on having your simulation results in a month ahead of time, ahead of the meeting.
Randy?
Yeah.
We have a date at this point, which is August 31st.
Oh, okay. Was that okay, that's even earlier than I was thinking. Okay. my fault. That's even better. And then but before too long, I recommend that you kind of get on to the website and any of the if you've done this before and you've submitted scripts and so on, please get on and update your repository, make sure that these all still run. There have been changes and updates to Python libraries and so on. I've tried to stay up to speed on that, but these things can kind of break your old configuration files and so on. It's better to sort of deal with that sooner rather than later. So that's all I had.
Okay. I don't see additional. Or is it planned to run more parallel antennas with the burner configuration? At this point, we are not running additional experiments in that setup right now. We have some intermediate scale stuff, but nothing that will be available, at least not before October. All right. We're getting close to 2. Are there final questions from anyone, either in chat or you want to just hop on and unmute yourself that we can work together? Alrighty. Given the silence, I'll apologize once again for whatever happened with WebEx, that we lost the ability to share video and screens. I want to thank Beth for stepping in and sharing that so we could still just follow through and finish the presentation. And to all of our speakers who prepared this, thank you for sharing your parts and making this possible. And thank you all for joining us today. We'll end with the final reminder. Please check that GitHub repo for most up-to-date versions of everything, and continue this conversation on the forum that we provided, the Google Groups discussion board that we have for each of these cases. Randy?
I just want to, Isaac, say thanks to you. For everybody who doesn't know, Isaac has been working very hard to get all this organized. So thanks a lot. Appreciate your efforts.
Thank you. Alrighty, take care, everyone. We'll see you soon. And modelers, we have some work to do. Please ask any questions. Otherwise, come June, we'll be nudging you to see those results. Take care.